Hey, this is Sue, and today we're going to talk about lesson 8.3, which is about finding area. Now, we've already talked about finding area. We've done it a lot with the definite integral, and we're going to use the integral again. But just a couple variations here. So one thing is that when you're asked in a problem to actually find area, they're talking about the geometric area of the shape. In which case, geometric area is always positive. Even though the definite integral will sometimes give you a negative number, geometric area is always positive. So if you're asked, for example, to find the area of the region enclosed by the graph of y equals sine x and the x-axis between x equals pi and x equals 2 pi, that's this region here. So keep in mind that the definite integral will give you an answer of -2, but you need to report an answer of +2 because they've asked you to find the area. So this is just important. We need to make our answers positive. We'll work that out together. Here are two regions to think about. This first one, we're going to look at this graph here, and we're going to talk about the region enclosed by the graph of y equals square root of x minus 1, the vertical line x equals 10, that's here, and the x-axis, that's here. So we're talking about this region here. The basic idea of how we're going to find this area is just like the definite integral was. We're going to cut this into rectangles and add up the area. So when we did Riemann sums, we did things like this. And we found the areas and we added them up. We also said that to get something really accurate, we were going to use little tiny rectangles, so thin that they just look like vertical line segments. So that's what we're going to do here. The second problem is a little more interesting. You're asked to find the region enclosed by the graphs of 5 minus x squared and y equals x minus 1. So that's this picture here, these two graphs, and so we're talking about this region. And this region isn't bounded by the x-axis, but we're still going to use vertical line segments. So we're still going to use little tiny rectangles. These rectangles are so thin, I'm drawing them really as just line segments. These are little tiny rectangles. And we're going to add them all up using the definite integral. So you have to pay a little more attention with this second example. The idea, and this is all written here, the idea is again that we're finding the area of the rectangle. The width of the rectangle is going to be dx, and the height of the rectangle is going to be the difference between the y coordinates. So for example, if we're looking at this rectangle here, the height is this distance here. We want it to be positive. So if you want to get a positive answer, you're going to subtract, but you're going to use the top minus the bottom. So in this case, for example, if this is y equals 5, and this is y equals -1, and you want to find the height, we'd really like the answer to be 6. You can do top minus bottom. And you'll do 5 minus -1, which gives you +6. We're not actually going to use these numbers because it varies. So instead, for the top, we'll use y equals 5 minus x squared. The bottom is always y equals x minus 1, but the key is that we're going to use top minus bottom. We'll show you this on the next page. But we'll end up with this kind of definite integral, where it's going to be the height of the rectangle times the width of the rectangle, and your width is going to be dx. And then we'll add them all up from x1 to x2, just like we do with the definite integral. So let's do these two examples. Same examples as before. Number 1, write an integral representing the area of the region. So there's a couple cross sections here. The top is always on the square root graph. The bottom is always on the line y equals 0. So your height is going to be top minus bottom, root x minus 1 minus 0. And your integral is going to be the height times the width of that skinny, skinny little rectangle. That width is going to be dx. And that's one representative rectangle, but we have to add them all up from x equals 1 until x equals 10. In our second example, as promised, we'll have vertical rectangles again, vertical slices we call them. The top is y equals 5 minus x squared. The bottom of each rectangle is on the red line, and that's going to be y equals x minus 1. So in this case, your height, top minus bottom, 5 minus x squared minus x minus 1. So my area will be the integral of the height times the width, dx again. And I'm going to add up all those areas from x equals whatever to x equals whatever. Sometimes you'll have to solve a system of equations to find those intersection points. I'm not going to worry about that right now. The intersection is actually at x equals negative 3 and at x equals 2. So that's how you set them up. We'll do 2 more examples.